Hi everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 10 of state space chapter basically. So in this chapter, right, in this lecture basically we'll learn the application of state space in electrical circuits, and we'll do few questions. So basically, right, in the previous lecture, what did you do? We basically find like the solutions, how to recover the transfer function, right? And from there we understand this also, that the eigenvalues of A will be poles of system. Okay, so this, right, the determinant of Si minus A will be the known as the characteristics equation. Okay, so yeah, that basically the summary I also summarized at the end of the lecture, also in the previous lecture basically. So now, right, what is the application of state space? Can you think of application? Like I told you, like in SFG, near the end I would tell you the application. So basically, right, it is also used to solve electrical circuits, complex electrical circuits we can solve, right? Why? Because, right, if we have RLC components, then we will get some differential equation, and state space is used to exactly solve that. It is used to convert higher order differential equation into single order and then solve that, right? So yeah, that's why it is used to solve electrical circuits. Also, like obviously it is used to analyze systems, that is already we know. Okay, so now, right, now like what are the electrical components? So mainly, right, we'll be concerned with electrical circuits which has only R, L and C. Okay, we will not be concerned with other non-linear components such as op-amp and like diode, all those things. We'll be concerned, we'll like strictly concerned with resistor, inductor and capacitor. Okay, so but for this, what we have to do is we have to, like when we solve the electrical circuits using state space, what is the first thing that we need to do? Think about it. The first thing that we need to do is to define the state variable basically. Which variables will be state variable? Okay, and remember from the first lecture itself, what does a state variable mean actually? What does a state variable do? The state variable is a variable which is responsible for the change of the state of the system. Okay, for changing the state of the system. Okay, so that is what a state variable is. So think of components out of these three, right, which will be responsible for changing the state of the system. I told you in the first lecture also, I think, of the state space, right? So which components will be those will be basically which have energy storing capability. Okay, so which components out of these three has the energy storing capability? So resistor, no, it can only dissipate energy, right? It can only dissipate energy, it can't store energy with it. Inductor and capacitor can store energy and then later change the state, right? Change the state. So the inductor and capacitor will be our state variable here. But one thing you might ask, that like if the energy is stored, right, if the energy is stored, then the circuit will act like non-linear. How I will show? Okay, but what we'll do is we'll assume the principle of superposition. Okay, like all those things I will explain it to you, but first, like, let me show you one example of why. Okay, so here, right, let's say my I have one capacitor. Okay, I have one inductor and capacitor, right? I have one inductor and capacitor. Now one thing is that, like, okay, I have this. Okay, so it's also, so I hope you have already studied the LC oscillator circuit, all those things. So this has some initial voltage of 10 volts, right? Initial voltage of 10 volts. Now what will be my differential equation equals to? So like C and L are those only. What will my differential equation equals to? So if I apply the like, let me mark the terminals. Okay, this is VC and let me mark this as VL. Okay, so if I mark the terminals, what do I get? So I have this 10 volts also here, right? I have this 10 volts also here, so I have to mark this 10 volts also, right? So the KVL, right, KVL, what I'll get is minus 10 minus VC plus VL equals to 0. Okay, this is the KVL, because this 10 volts is with this capacitor. I can, what I can do, I can like get this 10 volts out of this capacitor and place it here also. So that also you can do. Okay, that also you can do. Okay, so this is my differential equation. So now, right, now, like this is my VC0. So if I solve this equation, what is my VC equals to? VC equals to like IC equals to C dVC by dt. So my VC becomes minus 10 minus 1 by C integration of IC dt. Okay. Also my VL, right? What will my VL become? VL, right? VL will become L di dt. Okay. L di dt, which will be equals to 0. Which will be equals to 0. Now, right, due to this term, the whole equation is becoming non-linear. Okay, non-linear. So what should I do? So one more thing, that IC, right, this IC equals to IL only. IC equals to this IL only. Okay, so IC equals to IL only. So I will not be able to find very easily this IL, but this will become a non-homogeneous equation basically. How to make this homogeneous? What I will assume, this VC, this minus 10, right, I will assume this as VC0, right, constant. From there I will solve. This IC dt plus L dIL dt. Assume it as an input itself. Okay, assume it as an input itself, and then from there, this is a linear equation. This becomes a linear equation. Hence, I can apply the principle of superposition. Here. So I will find the, like, I can solve this in Laplace domain easily. Okay. So yeah, if like you couldn't understand this, it's not that important as per se. Okay, it's just to understand that if my circuit, right, if my circuit has some linear voltage, some initial voltage, what, like, we don't think of this that much because we solve it anyways, but the main thing is we apply the principle of superposition. We assume the capacitor to be 0 volts, and then some 10 volts is beside it, right? 10 volts is beside it. So that is what basically we do. So this was one thing to keep you in mind, is that how do you solve this? Okay, so what was the main point I was getting at here is that element, right, element that have the energy storing capability or that can change the state of elements, we'll choose them as state variable. Okay, state of system. So like what will be my state variable for LNC, right? So state variable, right, state variable, so whenever I see inductor, right, so my main aim will be to take the current as the state variable for inductor. Why? Because I will write the equation, from there you will understand. Current through inductor. So what is the fundamental equation? Fundamental equation is VL of t equals to L di dt. Okay, so inductor doesn't allow sudden change of its current, right? Also it is VL is depending on the differentiation of IL. So yeah, I can see that IL will be the state variable, right, that is defining this VL, right, voltage across the inductor. So this was my fundamental equation. This is my fundamental equation for the inductor. So inductor, how does it store energy? It stores energy like flux. And what is flux equals to? Flux equals to L times I. Okay, phi equals to L times I. Okay, so it stores energy in terms of current, right? That's why we define state variable for inductor for current. Okay, for current. Okay, now what will be state variable for a capacitor? For a capacitor, right, my state variable will be voltage. Why? Because it stores charge, right? Charge as energy. Okay, so voltage through capacitor. Voltage से क्या होता है? Okay, so yeah, this is basically now why is it voltage to capacitor? Basically, right, it is like what is the like current of the capacitor dependent on IC equals to C dVCT upon dt. So like how does capacitor store energy? It stores as charge, right? And like what is charge equals to? Q equals to CV. So it is dependent on voltage. So yeah, it stores energy as voltage. So hence our state variable will be voltage through the capacitor. Okay. So yeah, this is this is a basic thing. Now what we'll do is solve a few questions. From there our concept of how to represent, right, the state space representation of an electrical circuit will get more clear. Okay, this question is, take the screenshot and you do it by yourself. Okay, define the state variables for L and C. Okay, then define the current and voltage, and then you solve this. So here write the state space representation for the following electrical circuit. We haven't given the input as Vi of t and the output as V of t. Okay, and we have the voltages, right? We have the voltages. So these are the things. So now, right now, what is the question asking us to find is like this is the first question, that you have to find the state space representation. This you do, right? This you can do of the electrical circuit. You assume like state, how many state variables will be here? How many state variables will be here? There will be two state variables, right? So you solve the differential equation, find the state variable equations and the output equation. What is my output equation here? What relation can you see between a state variable and an output equation? That's the hint, right? So yeah, write the equations. That is good enough state space representation. Now what is the next question asking us to find is, if we haven't given initial conditions, like this input is 0, initial current is 0 through the inductor, but there is some voltage across the capacitor, right? There is some voltage across the capacitor. So what will be my RLC and values are given. Find the time domain expression for my state variables, that is basically Vc of t and IL of t. So they have also like given a hint that state variable will be Vc of t and IL of t, right? So yeah, let's first solve the part 1. So let me take the circuit. Okay, so like what is a step one is defining state variables. Define state variables. So what are the state variables here? State variables here are Vc of t and what is my other? IL of t, right? IL of t. Now my IL of t is equals to I of t only, because this is contained in series, right? So that you can do. Now you find out in terms of what you have to write. In terms of what you have to write the state variables. Okay. Define state equation. Okay. So what will be my state equation? So like I have to find this simple IL dot of t in terms of, as a function of what? As a function of IL of t itself, then Vc of t and also Vi of t. Okay, these three values I have to find. This is the input, right? So I have to find in terms of input also, and then I have to find the other variable, that is Vc dot of t as a function of, again the same thing, right? IL of t. Okay, this is Vc. Actually this seems like a VL. Vc of t and the V of t. Okay, so yeah, this is what I have to find the equations, right? Find the equations. So like one more thing I forgot to tell you, right? What will be the general convention that I will take for source and load. So let me explain. So this I forgot to explain you at that point of time. I just remembered this general convention for source and load. General convention source and load. So what is the general convention? The general convention is this one, right? plus minus, if I have a source, right, if I have source, okay, if I have source, like this is what I will generally take. If current is leaving, right, I will take it as like positive. Okay, I will take current leaving as positive. And if I take, like I have a load, right, I have a capacitor, so generally, right, this VC and IC relation, okay, is written like this, that in this case my ICT will be C dVc by dt. This capacitor is C dVc by dt. Okay, now one thing you have to keep in mind, if for some reason the current is in opposite direction, what I will take? I will take this as minus C dVc by dt. Okay, current is in opposite direction, that's why. So yeah, this was just a basic concept. I hope, like in network also you have Himanshu has taught you this, but still I wanted to like clarify this one. Okay, so yeah, I now I know this one. Now simply apply KVL KCL in the circuit. From there we will solve the circuit and we'll find out our equations. So first I will apply simple KVL, right? Simple KVL I will apply. Okay, if I apply simple KVL, what do we get? So instead of writing I of t, I will write IL of t. Okay, so first equation I know, I of t equals to IL of t. Okay, first equation I know. So again applying the KVL, what do I get? I get minus Vi of t plus IL of t r plus L dIL of t dt. Okay, plus this in terms of the state variable itself, I will not write I will not write IC by, I will write simply VC, right, because I have to write in terms of IL and like VC only, IL and VC only. Okay, so this will be VC of t equals to 0. So right, so what I can see here, I have my state, one of the differentiation of one of the state variables, and other variables are in normal format. So I can quickly like get one equation, right? One equation I can get is IL dot times L. I will put everything on that side. So this becomes minus R IL of t. This becomes minus VC of t plus V of t. Okay, again I divide by L. Okay, this is a state variable. This becomes minus R by L IL of t minus VC of t by L plus Vi of t by L. Okay, so yeah, this is my first equation, first state equation. Okay, so now let's solve for the next state equation. Okay, so this is IL of t. Okay, I hope you understand. If I don't even write bracket in t, right, so you get that this is IL of t. So what is my next state equation? So next state equation is VC dot of t. So like what is this value, right? What is the voltage across the capacitor, or what is the current across the capacitor? So one equation I know is C dVc dot dt equals to IC of t. Now in this case my IC of t equals to simply IL of t only, which is equals to I of t, which is like series network, right? So I can write VC dot of t equals to simply IL of t by C. So we have only one term this time. Okay, one term. So I can write the state equation. This is my first equation and this is my second equation. Just wait 1 minute, like it is raining outside, so I have to take the clothes. Yeah, sorry for the interruption, actually rain came, that's why. So this was my second equation. So let me write the state equations, right, in matrix format. So my state equation, what will be my state equation in matrix format basically? So this is the first equation, right, this one. So minus R by L minus 1. Okay, sorry, this is minus 1 by L. Okay, and so let me first write the equation, then I will explain it to you. So this, right, this is like minus R by L. Let me write, I will then explain. This is, okay, this is IL, so this is 1 by C, and this is 0 only. Okay, now this, right, this is, what is this? This is IL of t, and this is VC of t. And we have the input also. So input, right, like the input is only like the first state variable is only dependent on the input. So this is also 1 by L here, right? So 1 by L 0 and V of t. Okay, so this is my basically like the state equations, basically state equation matrix. So what do I see here? Like this is minus R by L times IL minus R by L times VC. So that is exactly what this is telling us, right? Minus R by L times IL and minus 1 by L times VC. And this one is like VC dot of t is 1 by C times IL and 0, right? So only one component is here. Okay, and this one, right, like there is one input term also which is multiplied by 1 by L, so we get this 1 by L, and for the second state variable we have nothing, right? We have nothing, so we get 0 only. So have you understanding how I about the state equation? We have done this multiple times, from differential equation to state equation. We have done this in the first few lectures, right? So yeah, that's why I went a bit fast. So now let me write the output equation. So what is the output equation? What is the output equation? So the output equation, right? So we have to write basically what is the output here. So the question has specified the output, right? V of t, right? So to write V of t in terms of the state variables and the input itself. So V of t, what is V of t equals to? V of t equals to VC of t only. Okay, so it's very simple. So V of t equals to VC of t. So there isn't any input, there isn't any other parameter. So VC of t itself is a state variable, so it's very easy for us to write the output equation. So in matrix format, right, V of t will be equals to simply 0 1, and this is my output variable. So this is IL of t and this is VC of t. Okay, IL of t and VC of t. Okay, and this is like now it isn't dependent on input. Okay, so this will be 0 only, 0 V of t. Okay, D matrix is 0, and this is my C matrix. So this is my C matrix, this is my E matrix, and this is my what this is my B matrix, right? So yeah, so I hope you are understanding how I'm doing this. Now let us solve the 20th question. This was the this was the 19th question. Let me solve the 28th question. So what does the 20th question tell us? The 20th question, right, it tells us that V of t equals to 0, IL of 0 equals to 0, all these are 0. Okay, but like there is some initial condition 1 volt. We have to find the time domain extension for VC of t and IC of t. So what help do we need? Remember, right, we are just doing this for the past few lectures. We need the state transition matrix. If you know the state transition matrix, I can find the values of the state variables. Okay, so for that I need the state equation. Okay, so this is my state equation. I will put the values of R, L and C in this equation, right? Okay, so like what is R, L and C? R, L and C are 3, 1 and 1 by 4. Okay, 3, 1 and 1 by 4. So this is replaced by 3 by 1, so this is actually 3. Okay, and this is 1 only, so this becomes 1 only, right? And C is 1 by 4. So what does this become? C is what, 1 by 4. Okay, C is 1 by 4. So this becomes 400. So this is my RL and C, and L is 1 only, so this becomes 1 again. This becomes 1 again. Okay, so like I think something I have done wrong, because I want to get to previous matrix, so I think this should be 2. Okay, so I think here, right, in the question I should have written here C is equals to 1 by 2. That is my mistake actually. Just notice, because I wanted to get to that matrix, right, -3 -1 2 0. Okay, so yeah, this one is, so my E matrix from here I can understand is this one, right? So what I have to do is find the Si minus A inverse. Okay, also let me take the initial conditions here also. Let me take this only, okay, because every time going back to this slide is difficult. So right, what will be basically my like phi of t, right? Phi of t. So to find phi of t, state transition matrix. So phi of t will be simply Laplace inverse of this Si minus A inverse, right? So Laplace inverse. So what I will do, first I will find Si minus A inverse as usual. Okay, so what is my Si minus A? It is S plus 3 S plus 3 1 minus 2 S. Okay, and this is the whole inverse, right? So again, if I take the inverse, I will get the determinant here, that is S into S plus 3 plus 2, and these are getting reversed, S into S plus 3, this is minus 1, this is 2. Okay, so this is my basically matrix. So again, right, before Laplace transform I will again do that xyz, right? Simple. So what I need to find is x of t, right? So what is x of t equals to? X of t equals to phi of t times x of 0. Okay, because our input is 0, hence my answer will only be this. Okay, so what I will do, simply multiply the phi of t with this, right? So phi of t, let me name this as a, b, c, d. And what is my x of 0? X of 0, like IL of 0 is 0 and VC of 0 is 1. So 0 1. My x of 0 is 0 1. 0 1, right? So like what elements I will get? I will get A times 0, B times 1. So the second column, right, I will get second column. So this is BD. Okay. So I need only these two terms, right? These two terms. So like what will be my terms? I have to take a Laplace inverse of let me expand this. This is minus 1. This is like S plus 2 into S plus 1. Okay, that's why I wanted to break this down like this. I had to change the value of capacitor, because this will come simple like in factor format, right? That's why. So and this, right, this is S plus 3 divided by S plus 2 into S plus 1. Okay, so S plus 2 into S plus 1. Okay, now I can expand this, right? Can again expand this, take the Laplace inverse. Let me bring this over here. So this, right, this is simply S equals to minus 2, S equals to minus 1. So if I put S equals to minus 1, what do I get? I get minus 1 over 1. So it is simply minus of e raised to power t, right? Minus of e raised to power t. So this one is minus only. Okay, now let me put S equals to minus 1 here. So this is like minus 1, sorry, S equals to minus 1 over here. This will be S plus 1, and if I put S equals to minus 2, this is minus 1 and this is also minus 1. So this becomes 1 plus s plus 2, right? This is what I get. Now this, right, this one, if I put s equals to my minus 1, okay, I get 1 by 2, so I mean 2 by 1, so this is 2 by s plus 1, okay. And if I put s equals to minus 2, I get minus 1 and 1, so I get minus 1 by s plus 2, okay. This is what I get, okay. So now I will take the Laplace inverse of this. My x of t will simply be equals to e raised to power minus 2t minus e raised to power minus t. This is 2 e raised to power minus t minus e raised to power minus 2t e of t, okay. So yeah, this is basically my expression for the state variable. So let me write this x of t, right? Let me write this x of t as like the state variables themselves. This is my IL of t, okay, Vc of t, and this is my IL of t and Vc of t, right? So these are my state variables basically. So like this was the answer for this the 20th question, right? So let's now move on to another question. So in this question, right, it has told us, instead of finding the state variable, it has told us to find the VO for the given state space equation. Find the VO, output voltage, for the given state space equation. The equation this time is given, right? The same equation as the previous one. Difference is this is only 1 times 0, okay, this is only 1 times 0, and the input this time is given, okay. Input is given 4 sine 2t, and we have to find the output basically, okay. The state space equation is given. So how you will solve it? So just think once that how you should solve it, right? So like if you thought like, yeah, I will first find the state transition matrix, or the then find the transfer function. Then after finding the transfer function, what I will do is simply do the Laplace inverse of this, then multiply with that, then find the output, right? Laplace of the output, then do the Laplace inverse again. So that approach is correct only, okay, but that approach is lengthy. So if you have studied signal systems, that's well and good. If you haven't, right, then like I will tell you one concept. Like if I have one LTI system, right, if I have one LTI system, okay, if I have one LTI system, and if I give this some sine function or an like a cos function, okay, sinusoid waveform and a cos waveform as an input, okay, and what will be my output look like? My output will simply be a scaled version of this sinusoid in magnitude and also in phase, okay. That's why we are so much interested in sinusoid signals and LTI systems. That's why we want to do simple analysis to the output, right? As I'm getting so simple format in my output. That's why we are so interested in LTI systems and in sinusoid signals. So that scaled version, if you remember some definition, right? Something is scaling, right? So what do we call the scale factor? We call the scale factor as eigenvalues, okay. So those are known as eigenvalues, okay, and like this input is known as eigenvector or whatever you want to say, okay. So yeah, what will be my scaling factor? My scaling factor will be simply the magnitude of the transfer function at that frequency, and the phase scaling will be the frequency will remain changed, the tone won't change, right? The frequency will remain changed. That's why this is a LTI system, okay. Frequency won't change. So this will be omega naught t only plus angle of phi of t j omega, t j omega naught, okay. So this angle will get changed and the magnitude will get changed, okay, but the frequency will remain same. So right, what is the simpler analysis? What I will do is simply find the transfer function, that is correct only. Then I will replace s by j omega, okay, as the real component is 0, okay. S can be written as sigma plus j omega. Now what I will do is like j omega naught in our case is 2 here, right? 2t. Okay, I will find the magnitude of the transfer function and I will find the phase of the transfer function. These things we have studied in like complex calculations we have studied in network theory classes. So yeah, that is what I will do. Okay, then right, then basically this tj omega, then simply we write the output expression. We don't need to do all those things, right? We don't need to do all those things, like again Laplace transform of this signal, then multiplying with the input, all those things, right? So yeah, let's first find the transfer function. So what will be my transfer function? So I told you one thing, right? You have to mug up one relation. What was that relation? That relation was C into SI minus A inverse times B. Okay, times B. So what is my SI minus A inverse? So SI minus A inverse is only that previous matrix only, right? Previous matrix only. So but this time I won't solve. Okay, again, like I will do C is 1 0, and again I will do A B C D, and again what is B? What is B this time? B is 1 0 again. So B is 1 0. So what we are doing is simply taking the first column, right? First column. Okay, first column I will get. So this is 1 0 only. Like simply I will get basically A, right? I will get basically A. This is A C. Okay, then I will multiply 1 with this and 0 with this, so this will become A only. So first element of the inverse of the matrix. So what is the first element? Like in previous I calculated the first element. Okay, this one was the first element, right? Yeah, this one was x of 0 multiplied this one, right? This one was the first element. So basically it is s times s square plus 3s plus 2. S by s square plus 3s plus 2. I will write in bracket from previous question. Okay, from previous question. Now this is my transfer function basically. Now what I will do? I'll simply replace s equals to j omega naught, and omega naught in our case is 4 radian per second. So omega naught in our case is 4 radian per second. So what I will do? So this will become j. Okay, so not 4. Sorry, it makes a mistake. Okay, sorry. This is 2 radian per second. See, like this silly mistakes can happen with you too. Just be careful. Okay, this is 2. So let me take few pages actually. This is like j2, right? S j omega naught I am replacing, and inside is s square. So s square j2 whole square, what is it? Minus 4. So this is minus 4, and this is like then we have 3s. So this is 6j only. Okay, like 2j times 3, 6j plus 2 is 2 only. Okay, now we are left with like I can take 2 common. Okay, so this will be simply minus 1 plus 3j, right? Minus 1 plus 3j. Okay, now like from here I have to find the magnitude of transfer function and the angle. So magnitude is easy only. What is like my magnitude of t of j omega? It is simply equals to 1 by 1 plus 9 under root. So it is simply equals to 1 by under root 10. Okay, so this is my basically magnitude, right? So this is easy only. Okay, now what is the angle of t j omega? This is a bit complex, so I'll go into the next page. So my angle, right? My angle is basically this one is 90 degrees only. Okay, numerator is 90 degrees only, so this will come as 90. Now to subtract tan inverse, what upon what, or do I have to simply subtract tan inverse? So this, right, like this is the whatever is in the numerator, we like add the angle, whatever is the denominator, we subtract the angle. So what is this angle? Like this, what I can observe is this is in the which quadrant? This is in the second quadrant, right? Because the real component is negative, so I'm in this end, and the imaginary component is positive, so I will be in this quadrant. So what is my angle at this point? So if some vector is here, right, the angle is, this is theta. If this is theta, then this is 180 minus theta. So all these things in network theory you will understand, right? I have already taught you. Very good. Okay, so yeah, I'm lying in the second quadrant. Okay, so this, right, this will become 180 minus theta. So this is 180 degree minus tan inverse of y upon x. Y is 3j, like 3 only. Okay, imaginary component upon the real component. So like I've already calculated it. Like you should also remember this. What is tan inverse 3? Tan inverse 3 is 71 degrees. So this is 90, this one minus 90, this becomes plus 71 degrees. Okay, so around 71 only. Okay, and around the answer that I am getting is 18.44 degrees. Okay, yeah, 18.44 degrees. I've already calculated this one, 18.44 degrees. So what will my output expression will look like? So my output, right, it is 4 sine 2t input, so it will be multiplied with the magnitude, which is 1 over root 10, and phase shifted by 18 degrees. Okay, you can convert this into radians, put there, but whatever you want to do. Okay, I'm writing here in terms of degrees. Okay, so yeah, so this is the solution for this question. So let's solve another question. This is a bit difficult actually. So we have to write the state space representation of the following circuit. This is simple only. Okay, state space representation I can write, but in the next question what you have to do draw a state space diagram. That will be difficult. Okay, so state space representation. So first, right, you see, now you take the screenshot. You have to write the state space representation. Take the screenshot and think, what will be my state variables? How many state variables are here? Okay, and like how will I define it? So let me take the circuit and try to solve the question, right? So what are the state variables? So let me first write all the variables, right? So this is my Vi. Okay, let me name this as Vc1. Okay, so yeah, let me name this as Vc1. This is VL2. Let me name this as IL2. Okay, we have only L, so why am I naming this L2? I don't know. So let me name this as L only. Change the question. This is only IL. Okay, and convention is a current is coming into the node, right? Positive terminal. That is my general convention that I already explained it to you in the starting of the video. So this is IC2 of t. This is IC1 of t. Okay, this is Vi of t only. Okay, now let me name, what is this current? What is this current? This current is simply, what is the potential here? The potential here is Vc1, right? Vc1. So this current is simply Vi of t minus Vc1 of t divided by R1, right? So this is this current. Now this current is getting divided into two of these currents. Okay, now what is this current? This current is again, the voltage is VL2. This is only VL only. So VL by R2. VL by R2. Okay, VL by R2. So yeah, this is simply VL by R2, and V0 equals to VL2 only, right? But that is not a state space relation, so I will not write that. So now, right, can I write this in terms of state space variables. Can I write this? So one thing I know, like what is, like, this is IC1, okay, this is IC2. So like IC1 plus IC2 is this one only, right? IC1 plus IC2 is this one only. So what I can do is I can subtract, like okay, what is wrong here is this is one thing I know, IC is C dVc by 2. Okay, so yeah, let me write the equations, then we'll solve this. So this is, first let me like write this circuit, then we'll solve. So this was the step 1. Draw the circuit. Draw the circuit, right? So what will be my state variables here? Let's first name those. Okay, so my state variables, right, like one will be VC1. Okay, voltage is always state variable for capacitor, and they are independent, right? Always, if you want to take the minimal set, so you see the, like, voltages are independent. Okay, capacitor are independent. That Himanshu has already taught you, right? So VC1 is independent, VC2 is also independent, and I have IL also, data current also. So these will be my state variables. So what can I do? The first equation that I can write is this KVL, right? This KVL. So I will get the state variable in terms of this one. So how? So if I write the, like, the middle KVL, what I will get is KVL is minus VC1 plus VC2 plus VL equals to 0. Okay. So what is what is our simply, like VL equals to L dit dt minus VC1 plus VC2 plus L dIL of dt. So here, right, I have IL as a state variable, okay, and I'm getting it in terms of VC1 and VC2, other state variables. So I'm getting the first equation. So my IL dot of t will be equals to VC1 by L minus VC2 by L. Okay, so this is my first equation basically. So this is what I get, IL dot of t. Okay, so what else can I do? So like I have to find, like, VC1, right? I have to find VC1. So what I can see here is, what is this IC1 equals to, like this IC1, right? This IC1 is, this current is incoming and this current is outgoing. Okay, this current is outgoing. So that is what IC1 equals to. But one more thing, what is this VL equals to? This VL, what is this VL equals to? This VL, right? VL is equals to this one, right? VL is equals to this one. The subtraction, like let me write here. So this is what you have to do, like do the heat and trial method and solve for each like circuit parameters, find the voltage currents all across this. Then you go, like, you can't just go it like smooth flow, like, yeah, I know this, and yeah, this will be it, right? Okay, so VL will be equals to VC1 minus VC2. Okay, VL will be equals to VC1 minus VC2. So this one, right? So this VL is VC1 minus VC2. So here, right, I can write this in terms of state variables. So this VL I can replace as VC1 minus VC2. Okay, VC1 minus VC2. So here, right, I am able to write the output in terms of state variables. Okay, also, right, what is the current through this one? What is IC2 equals to? IC2 is IL plus VC1 minus VC2 by R2, right? So let me write here different color. IC2 equals to VC1 minus VC2 divided by R2 plus IL, right, plus IL. Okay, so now, right, this is what will help me find the basically like this is what this is C dvc by dt. So this is C2 dvc. Okay, let me copy this only. Okay, I will dvc2 by dt. Okay, copy this only, change the color of this one. So here, right, if I just divide by C2, I will get my desired equation, like another state variable Vc dot of t is equals to Vc1 by R2 C, simply CD by C equals to CD, yeah, Vc by R2 C2, and this is minus Vc2 by R2 C2 also, okay, plus IL by C2 only, okay, plus IL by C2 only. So this is my like the third equation that will come. Okay, this is my third equation basically. This is my third equation. So it doesn't matter, it matters like what sequence you are taking. So I'm taking like this sequence. So this will be my second equation. Okay, so this will be my second equation, and this will be my third equation. Okay, you might find any of the equations first, that doesn't matter, but how I'm writing the matrix form, right, that is important. Okay, so what is my x1 of t, x2 of t, all those things, that's why I'm writing it like this. Now we have to find the this, right, this capacitor. So right, what like I was doing here is, like whenever you have to find the capacitor state equation, right, you write it in terms of current, then you convert the current, capacitor current, in voltage. So I get the differentiation term in the voltage, and other things I get in normal format, right, other normal format. Okay, so yeah, that is what for you have to take in mind for a capacitor, right. You have to write in terms of current, and for an inductor, right, what you have to do is write in terms of voltage, because voltage equals to L di dt. Later you will replace the voltage in current format. Okay, so this is the trick that you have to keep in mind. Okay, this is the thing that you have to like keep in mind while solving the question. So like what is IC1 equals to, that's why I'm writing here current. What is IC1 equals to? IC1 simply is equals to this current subtraction of IC2. So this is VI minus Vc1 by R1, Vi of t minus Vc1 of t by R1 minus IC2, right, minus IC2, right. But like now right now, like what will be like my IC2. So IC2 I have already derived here, right, IC2 I have already derived here. So these are in terms of state variables only. So I will just copy this and paste it here, so I can copy paste everywhere. Okay, so this is minus, and this also minus. So it's understood, right, all this is like in brackets in t. I hope you're understanding. Just in exam also you don't need to write bracket t. Okay, who is seeing so this is simply so this is related with input also, so I will bring this forward. Okay, this is Vc1 by R1, okay, and this is in minus sign, and this is C1 dVc1 by dt, and this is plus Vi of t by R1. Okay, so like what is this? So this, right, this is Vc1 dot equals to, simply I will take Vc1 common here. Okay, Vc1 I take common. Okay, this is minus R1 by C1 and minus 1 by R2 C1 plus Vc2 by R2 C1 minus IL by C1. Okay, and this is Vi of t R1 C1 basically. Okay, so yeah, let me reduce the size of this, because this color is also contrasting. Yeah, so this is my like equation, right. So this is like a very big equation actually. So this is actually Vc2, Vc1, Vc2 minus R1, yeah, C1 is common only. So yeah, this is my equation. So now I will write the state space matrix basically. So what I assumed was VC1 was my first state variable, VC2 was my second state variable, and IL was my third state variable. So VC1 so what will be my equation? So this, right, this I can convert this like this one. This is minus C1. I can take the C1 minus C1 common, and this will become 1 by R1 plus 1 by R2. Okay, and like this one, right, this is 1 by R2 R2 C1. So this is 1 by R2 C1. I have to reduce the space actually. Okay, and what do I have to do? I have to simply this last term, right, this is minus 1 by C1. So let me first write this, like you will understand by yourself also. So like the second equation is this one. So this is 1 by R2 C2. Okay, let me not write like this. Let me write this. And this is minus 1 by R2 C2. You may not understand this. What is this? R2 C1 I should write here. C1. This one was minus R2 C2. And this is 1 by C2 again. So I think I have to like reduce the space like the size of this one, so that I can fit this in a single line, right? So like I have to like decrease this here, decrease this here. Sorry for the inconvenience. So this is like this one only. So let me bring this a bit down. And what will this become? Third equation was simple only, right? Third equation was this one. This is 1 by L minus 1 by L, right? And 0. And 0, right? And like this is my state variable basically. This is my VC1 and this is my VC2 and this is my IL, right? So I hope you are understanding. These are in terms of time only, so I still have to write time only. Okay, now I will write the input value, right? So what was my input matrix? So input, only one state variable is depending on this one, right? 1 by R1 C1. So like the VC1, right? So this, right, this will become 1 by R1 C1 0 0. This is my Vi of t. Okay, V of t. So yeah, this is basically my V of t. And what is my V naught of t? So V naught, right? So V naught of t equals to V of t only. So let me write here also. V naught of t equals to VL of t, which is equals to VC1 minus VC2 that we calculated earlier. So how can I write V naught of t in terms of VC1 and VC2? So again, right, so let me take a different color this time. Okay, let me write this in big only. V naught of t equals to simply 1 minus 1 0, and this is my state matrix, right? This is VC1 of t, VC2 of t, and IL of t, right? So this is my output equation, this is my state equation. So let me write this here. Sorry, this is my okay. So yeah, this was the solution for this question. Now let's solve another question. So in this question, right, so this is a big question. What I will do is I will give this question homework for you, and you do it. Okay, like this you can do, right? This you can do. Find the state space representation for the following circuit. This you can do. Okay, but like what thing you have to keep in mind: for capacitor, always try to write the current. Okay, current, and for inductor, always try to write the voltage in terms of other state variables. Again, how many state variables will be here? You guess, right? So but this is the more interesting question. Like they have given us the state equation. Okay, they have given us a state equation. You have to find the values of xyz. Okay, match with that. Okay, match with that xyz. You write the state equation matrix, you match xyz, and also write like the state. Okay, they have given the state variable, so now the hint is gone. So this is like the i1 dash, like i2, this will be i2 dot, and this will be vc dot, right? So I hope you understand why. For obvious reason, one capacitor and two inductors. Okay, so yeah, they have given us the state equations. Basically you have to find the value of xyz. You do that. Okay, this hint is already given. This may come in a question, gate question, right? And that's why you have to find xyz. Also find the values of r1, l1, l2 and c, because this A matrix, right, system matrix, will come in terms of r1, l1, l2 and c. So you find the values. Also the final, if you aren't able to do it, that's fine. The final thing that you have to do is draw the state diagram. Okay, this will be a bit different, not like previous cases where we draw the state diagram. I'll show you, like explain it to you how to draw the state diagram. So this you can leave, but these things you can do, right? So yeah, this is the homework for this lecture basically. So in this lecture we understood what is the application of state space, right? We can easily simplify big, like multiple integral differential equations into simple state space matrix, and from there I can get my output expression, or the state variable expression also. So these are very important, right? These are very important. So yeah, that's how this easy it is, right? However big my circuit is, I can still easily find my state space matrix, and then I can easily simplify and get the expressions for whatever voltage currents I want to get, right? So that's why this is very useful method. Okay, so yeah, thank you for watching, and see you in the next lecture.